Hello students, this is part 2 of the distribution of sample means. In this case, we're going to describe the distribution of sample mean for non-normal population. The following table and histogram give the probability distribution for a rolling of a fair die. As you see here, we have the histogram, which shows a distribution that is not bell-shaped, so it's not a normal distribution. It's more of a uniform distribution. We computed the mean. The mean was 3.5 and the standard deviation was 1.708. Note that, again, this distribution is not a normal distribution. We want to estimate the sampling distribution of the sample mean by obtaining 200 simple random samples of size 4 and calculating the sample mean for each of these 200 samples. We're going to repeat that for samples of size 10 and then samples of size 30. And as we do that process, we're going to create a histogram for the sampling distribution of the sample mean for each of the sample sizes that we came up with. So the next few slides are going to show the histogram that we created from sample 4, sample 10, and sample 30. So here is the histogram that was created for sample means from samples of size 4. And as you can see, it is approximately normally distributed, but it's not exactly normally distributed. As we increase the sample size, notice how the tails develop more, so we have more of a normal distribution. And again, if we have size 30, you will see the shape develops more tails, and now we have a more normal distribution. So we can conclude a few things from here. While we still have the same information that we learned about the sampling distribution of sample means, the mean of the sampling distribution is equal to the mean of the parent population, and the standard deviation of the sampling distribution of the sample mean is still the population standard deviation divided by the square root of the sample size, regardless of the sample size. So if you do the computation, you will find that we still have the same information for a normal distribution. So regardless of the sample size, we still have the same information. The shape of the distribution of sample mean becomes approximately normally distributed as the sample size increasing, regardless of the shape of the underlying population. So we started with a population that is uniformly distributed, and then we ended up, when we take the samples of a specific size and then compute the sample mean and then create sampling distribution of these sample means, then we create a normally distributed distribution. So in short, the distribution of sample mean is going to be normally distributed regardless of the population, whether it was normally distributed or not. And that leads us to the center limit theorem. So the center limit theorem for means, in this case, says that regardless of the shape of the underlying population that we're sampling from, the sampling distribution of sample mean becomes approximately normal as the sample size n increases. So in other words, if you have a sample of size 30 or more, you're going to assume that the sampling distribution of sample mean is approximately normally distributed. Let's look at a simple example to apply the center limit theorem. Suppose that the mean time for an oil change at a 10-minute oil change joint is 11.4 minutes with a standard deviation of 3.2 minutes. If a random sample of n is equal to 35 oil changes is selected, describe the sampling distribution of the sample mean. In other words, compute the mean and the standard deviation. So in this case, notice how the sample size is greater than 30. So we're going to, since the sample size is big enough, greater than 30 is considered big enough, we're going to assume that the sampling distribution of sample mean is going to be normally distributed, and as such we can apply the normal distribution rules that we know to this distribution. and we can compute the mean and the standard deviation for this distribution, or the standard error. So we know that the mean is equal to the population mean. The mean of the sample mean is equal to the population mean, which is 11.4. And then the standard error for sample mean, or the standard distribution of sample mean, is the population standard deviation divided by the square root of the sample size, which is in this case 3.2 divided by square root of 35, and it gives you 0.5409. So now we computed the mean and the standard deviation for this distribution, or we described this distribution. The second part of the question is asking you now, if a random sample of size n is equal to 35, notice how the sample size did not change, so we do not need to compute a new standard deviation. We can stick to the original standard deviation that we computed in the previous slide. So we say if a random sample of n is equal to 35 oil changes is selected, what is the probability that the mean oil change time, you see how it's asking about the mean oil change time, is less than 11 minutes. In other words, it's asking what is the probability that the mean oil change time is less than 11. It's not asking about the change time. It's asking about the mean oil change time is less than 11. In other words, we're going to use the distribution of sample mean. And since we know that the sample size is big enough and the distribution of sample mean will be normal according to the center limit theorem, then we can apply the rules of normal distribution that we learned about in week 8. So now we need to standardize the 11. Remember, you can do that immediately in Excel. However, I would like you to do the 4 steps that are required, which is standardizing, and then you're going to write the formula and then find the formula and then explain the results. So I'm going to standardize the 11. You can use the function standardize on Excel instead of doing it manually like I do it here. So the z-score for that number 11 is going to be the x, which is the number 11 here, or x bar in this case, minus the mean. We computed the mean previously, so the mean of sample mean was 11.4. So that is the mean of the sample mean, and then divided by the standard error, or standard deviation of sample mean. This is going to give us a z-score of negative 0.74, which means if we want to compute the probability, now the x bar is standardized, it becomes z less than negative 0.47, which is the standardized version of 11. Now on Excel, you're going to say it is going to be norm.s.distribution of negative 0.74, comma, true. And then that is going to give you approximately 0.23. So if you plug that into Excel, it should give you that answer. So we're applying what we learned previously. However, because we have a sample size, we will need to come up with a new mean and a new standard deviation for the distribution of the sample mean. And that concludes the distribution of sample mean. If you have any questions, please let me know.